this question. A spherical steel ball with volume 0.05 meters cubed experiences a drag force of 40 newtons. If the volume is doubled, what will happen to the resistive force? Obviously, the resistive force is the drag force. I just changed the wording because I want you guys to get used to it. The exam always does that. It changes the word. But I know for a fact that the resistive force is the drag force, it's the frictional force, it's the viscous drag. They all mean the same thing. It's F equals 6 pi eta VR. So yeah, I'll give you 3 minutes to do this question, or 2 minutes. Okay, any progress? How did you start, Lisa?
So I wrote down the formula F is equal to 6 pi. And then the viscosity of liquid, I don't know what you call it, and then RV.
Eta VR, good.
Eta VR. And then so from the equation you can see that the force and the volume are directly proportional.
Oh, is that the volume? You just said velocity. You're
Oh, that's the
contradicting yourself.
velocity. Oh yeah, okay.
Good start. Think about it. Anyone else?
Wait, so I think I can like carry on off of his Sir, if the volume of the steel ball is doubled, doesn't that mean the radius is doubled?
Well, good question. What is the relationship between volume and radius?
I don't know, sir, but like I'm thinking of it as like a circle with like, and then the radius of the circle obviously has to get bigger if the volume of the circle became bigger. So that's what I'm thinking.
I agree with you. Very good. However, it's not very physicsy of you because you do know the equation for volume. So you do know the relationship. What's the equation for volume of a sphere? Because this says a spherical ball. And remember that Stokes's law only applies for spherical objects anyway. This is one of the assumptions of Stokes's law. So you only ever do this law, this 6 pi eta VR, when you're talking about spheres. So what's the equation for
sir.
the volume?
I think, is it 4/3 pi r?
No, very close. 4/3 pi
4/3
r,
pi r cubed.
pi r cubed. Excellent.
Oh, okay.
So how is volume related to radius? Volume is proportional to radius cubed. Okay, so now what? I know the relationship between volume and radius. How does that help me?
Sir, since you know the volume doubled, you can find the radius by doing 2r in brackets and then all of it cubed.
Close? Okay, so going back from Stokes's law, what's going to help me answer this question is I need to know what the relationship is between force and volume, correct? Because I want to know what happens to the force when the volume changes. But to do that, I need to first know what the relationship between force and radius is. And I know that force is proportional to radius because radius is the only thing in this equation that is linked to volume. So force is proportional to radius. But how is radius related to volume? So radius is proportional to, let's cube root both sides of the equation. So cube root of the volume. That is how the radius is proportional to the volume. Does everyone follow so far? If anyone's confused,
Yes,
now's
sir.
the time. This is going to get more confusing. So the radius is proportional to cube root of the volume. I just got it from this equation. Therefore, if force is proportional to radius and radius is proportional to cube root of the volume, that means force is also proportional to cube root of the volume, because force is proportional to radius, and look, radius is proportional to cube root of the volume, meaning force is proportional to cube root of the volume. Now I have the direct relationship between the force and between the volume, which is what I want because I'm given the force and I'm asked what happens when the volume is doubled. So now what I just do is instead of V, I write 2V because the volume is doubled. So force is proportional to cube root 2V. Therefore, force is proportional to cube root 2 multiplied by cube root V. I'm sure you've done this third rule with Mr. Khan. So what's the relationship? The relationship is cube root of 2. That's the coefficient, okay? That's the factor. Remember before the factor was 4V because it was 2V squared, so that becomes 4V squared. So the factor was 4. Now the factor is cube root of 2. So what I have to do is I have to multiply the initial force, which is 40, multiplied by cube root of 2, and you get around 50 something. I don't know. I am not a calculator. Let me check. 40 times cube root of 2. Oh, you get 50.4. I guess I am a calculator. 50.4, and the unit is newtons. Okay, raise your hands if this makes sense. Ooh. Okay, shall I give another question? Or shall we move
So
on?
you can just re-explain this part again.
Okay. Let's do this quickly. So start off by writing down the equation, 6 pi eta VR. The volume is doubled. Well, this equation doesn't contain volume, but it does contain radius. And I know that radius is linked to volume via the equation. V is equal to 4 over 3 pi r cubed because it's a sphere. Therefore, the volume is proportional to radius cubed, or the radius is proportional to cube root of the volume, right? And everyone told me that they're happy with this step so far. So I know the relationship between the radius and the volume. And I know from this equation that force is proportional to radius, but I also know that radius is proportional to cube root of the volume. Therefore, the force is proportional to cube root of the volume. What happened to the volume? The volume doubled. So I'm going to write force is proportional to cube root of 2v because the volume doubled. So there's a factor of 2. Now I'm just going to use the simple rule AB square root AB is the same as square root A square root B, or even cube root AB is equal to cube root A cube root B, or whatever the power is. This is a third rule, okay? So that's what I'm going to use now. So that becomes force is proportional to cube root 2 multiplied by cube root V. Initially, I had force is proportional to cube root V. Now I have force is proportional to cube root V multiplied by some extra factor. So this is how much, this factor is how much your force increased by. So your force increased by cube root 2. So if my force was initially 40 and it increased by this factor of cube root 2, I have to do 40 multiplied by cube root 2, just like you did 1,200 joules multiplied by 4 in the previous question. Now you're doing 40 multiplied by cube root 2, and you get 50.4 newtons. Does that make sense?
Yeah, I got it.
I'll give you guys one more question. One more question. A tennis ball of diameter 0.12 meters experiences a air resistance of 120 newtons. This one's going to truly test a lot of your understanding. And in fact, this question is really good because you'll see why. The speed of the tennis ball halves. Work out the new drag force acting on the tennis ball. Have a go at this. That's not how you spell halves. Whoops. I'm so sorry. This question was flawed. I don't know why it was speed. I'm supposed to write the volume.
Yeah, so I was really confused.
Yeah, sorry. I'm very, very sorry. So the volume of the tennis ball halves. Work out the new drag force. Probably wondering, how does the volume of the tennis ball randomly half? Doesn't matter, just assume it happens. Okay, any progress?
So I don't know if I'm doing it correct, but I got to P is proportional to 1/2 volume.
Okay, so what equation are we going to use? How are we going to start this question? With what equation?
So yeah, we're gonna start the question with F equals 6 pi.
Good. You might be wondering, hang on, but there's no fluid. Well, actually, air is a fluid. Air is a fluid. So you can use viscous drag. This is viscous drag for spherical objects moving through a fluid, and both liquids and gases are fluids. So something falling through the air will also have viscous drag. So good. And you want to know what happens when the volume doubles. So again, there's no volume here. There's only radius. So I had to do volume is proportional to radius cubed. Therefore, the radius is proportional to cube root of the volume. Who's reached up to this?
Me. Yes,
Good.
I got to there.
Carry on then, Isa.
So then I wrote down a force is direct proportional to the radius. And so because the radius is directly proportional to the cube root of V and force is directly proportional to radius, we could also say that force is directly proportional to radius and cube root V.
Good. So force is proportional to cube root V. Excellent.
A half V actually, because a half V.
Yeah, no, this is the general rule. This is the general rule. Now the volume halved, correct?
Yeah.
So the volume halved. So you're going to do force is proportional to cube root 1/2 V. Carry on.
Yeah. So force is directly proportional to the cube root of a half multiplied by a cube root of V.
Excellent. So now we have the factor. Excellent. And what is cube root of a half? Does anyone know? Cube root of a half is the same as cube root of 1/cube root of 2. But
So
yeah,
it says 0.79 on a calculator.
Yeah, 0.79. That is the factor. So now you just do 120 multiplied by cube root for half, because your initial force is 120 and the factor it changed by, I don't want to say increased because in this scenario it decreased. And yeah, so you multiply it by this factor and you get whatever answer you get in your calculator. Does that make sense? This is from the hardest of questions, the one involving the volume change for the force change. Generally, it's not that hard, but what I want you to notice in the future is sometimes you're not given all the variables, but I know that once something doubled or something halved or something increased by a factor of 7, you will get at least one of these questions in your exam, 100%. So just be prepared. This is the sort of stuff you need to do. Write down the equation. How does this variable depend on that variable? What's the factor? And then multiply by that factor. Always the same steps. Okay,
Sir?
Yes.
So, sir, the answer I got was 95.2, but what is the units that you used?
Well, it was force, so it's newtons.
Okay.
Also, sir, why do you multiply it by 120? Because the last time we added it, not multiplied it.
No, we didn't add it. We multiplied it. We did 40 multiplied by cube root 2.
Oh, but sir, why do you multiply it? That's what I'm confused about.
You multiply it because when we said force is proportional to cube root of the volume or cube root of half the volume, that became force is proportional to cube root half cube root volume. The reason you multiply because originally force is just proportional to cube root of the volume, right? This is the original. But when the volumes are half, the force becomes this multiplied by cube root of the volume. So when the volume halved, the force changed by this much. Because now you have to multiply this by cube root of the volume. And because the force changed by this factor, and the force was initially 120, you have to multiply 120 by this factor. Does that make sense?
Yeah, I got it. Thank you.
Yeah. That's how much the force changed by when it halved. Likewise, if, I don't know, the volume tripled, so the volume, no, let's say the volume increased by a factor of 9. So this becomes cube root 9v. Therefore, force is proportional to cube root of 9 cube root of v. So force is proportional to 3 because cube root of 9 is not 3. I was trying to be clever, but let's say cube root of 9 multiplied by cube root of 3. Sorry, multiplied by cube root of v. You're going to have to multiply 120 by cube root of 9. So whatever that factor you get out, that extra factor that got introduced once you change the volume, that is the factor you have to multiply your answer by. Yeah, and it's always like that. So that is why I told you can't just think of it as, oh, this doubled, therefore it's 2 squared, because you might have something like this. So you have to actually do it properly. Let's continue with the lesson. It's not the lesson, it's the lesson. So let's talk about terminal velocity. Let's say you have a ball, and just before the ball touches the liquid, the only force acting on it is weight. Let's say it wasn't moving, and you held the ball just above the liquid. Okay, the only force acting on it is weight, mg. And as the ball starts to enter this liquid, and it's all the way inside the liquid, and it keeps accelerating because there's a force of mg. But as it gets faster and faster, the force of drag starts to increase until the forces are balanced and it reaches terminal velocity. Now, my question is, what are the forces acting on the ball when it reached terminal velocity inside the fluid? What are all the forces acting on it?
So you're gonna have weight acting downwards and upthrust acting upwards.
Okay, weight acting downwards, upthrust acting upwards. Is that it? Are we missing a force?
The viscous drag force, viscous drag.
Also
well.
acting upwards, right? Because it's moving down, and friction always acts in the opposite direction to the movement. Good. So you have weight going down, you have upthrust up, and you also have the drag force, the friction force up. And these forces are balanced because it reached terminal velocity. Just a quick reminder from Newton's second law, when the forces are balanced, there's no resultant force. Therefore, there's no acceleration. If the acceleration is 0, it's not going to speed up and it's not going to slow down, meaning it's going to remain at constant velocity. And this is the terminal maximum velocity it reaches. Okay, so
Yes,
what
sir.
is, yes?
So if it's at terminal velocity, it would be W equals F plus U.
Excellent. And that's what this question is. So what is the resultant force acting on the ball? The resultant force acting on the ball is W is equal to F plus U. The forces down is equal to the forces going up. Lovely. So let's do that. The upwards forces, downwards forces. So U plus F is equal to W. What is the equation for upthrust? mg, right? The weight of the fluid. And the weight, the mass of the fluid is density times volume. So upthrust is the mass of the fluid displaced. In this case, it's water. So the mass of the water, W stands for water. So the mass of the water times by G, because remember, what is upthrust? It's the weight of the fluid, weight of the water displaced. And what is the weight of the water displaced? It's the mass of the water displaced multiplied by G, plus the friction, or the viscous drag, which is 6 pi eta VR, and that's equal to the weight of the ball. Not the weight of the fluid displaced, the weight of the ball. And the weight of the ball is the mass of the ball, so m times b multiplied by g, because weight is m times g. So does it make sense what I did so far?
Yes, sir.
Good. Now I have a question for you. I'll be so impressed if someone could do this. Really and truly, it's just a bit of rearranging. Can you manipulate the above equation to arrive at the following equation for the terminal velocity? Well, I know the terminal velocity is when the weight plus the friction is equal to, sorry, the upthrust plus the friction is equal to the weight. So now I have to rearrange to make the velocity the subject, and this is the terminal velocity because the forces are balanced. And after you make the terminal velocity, the V the subject, can you somehow change it so it matches this form? So have a go. I will give you all 5 minutes. And by the way, you do need to know how to derive this for your exam. If you're wondering what does PB and PF stand for, PB is the density of the ball, B for ball, and PF is the density of the fluid. In this case, the density of the water. So that's what these two variables mean. Where did they come from? Well, that's your job to figure out.
Sir.
Yes.
So the volume of the water, is it like in a cylinder, or what's the
Oh,
shape
this
of the?
this is not the volume of the water. Will be the volume of the water displaced, because upthrust is the weight of the fluid displaced.
Oh yeah, okay. Oh, okay.
Okay, did anyone make any progress? We'll like do this in steps.
So I made a bit of progress.
Okay. So let me start by screenshotting this. Tell us what you did so far.
So first, I moved m water G to the other side, so it became mbg minus mwg.
Okay, good. Mass of the ball, G minus W. G, then what did you do?
And then so mass is density multiplied by volume. So then I wrote down. Oh no. Then wait. Oh yeah. So mass is density multiplied by volume. So I wrote PB VBG minus PW VWG.
Good. So mass is
Over.
density time volume. So let me just explain this for everyone. Mass is density time volume, meaning the mass of the ball is equal to the density of the ball multiplied by the volume of the ball, and the mass of the fluid displaced is equal to the density of the fluid multiplied by the volume of the fluid. Why did he do that? Well, if you go look back at the equation, what must have happened is he must have saw that this equation contains density of the ball and the density of the fluid or density of the water. So where can I get density from? Oh, I'm given mass and I know that mass is density times volume. So excellent. So now you substituted that in, right? But what I would advise is before you substitute it in, make the velocity the subject, just to keep things a little bit more tidy. So to make the velocity the subject, because that's the goal, divide the other side of the equation by 6 pi eta r. So this becomes velocity is equal to mass of the ball G minus mass of the fluid G over 6 pi eta r. Okay. Now it's
So that was
starting
my
to
next
look a
step.
little bit similar because there's an eta in the bottom here. There's an eta in the bottom here. So I'm getting a little bit happy. Now continue. So you're going to substitute these two in, right? So the velocity is equal to, well, mass of the ball is the same as the density of the ball times by the volume of the ball. And by the way, the volume of the ball is the same as the volume of the fluid displaced, right? From Archimedes' principle.
Yeah.
Remember, if you have like a container full and you put an object, water is going to be displaced. And the volume of the water displaced is the same as the volume of the object. So I don't need to write VB and VF because VB and VF are the same. So I'm just going to write V. So the density of the ball multiplied by the volume multiplied by G minus the density of the fluid or water, whatever you want to do, the density of the fluid multiplied by the volume multiplied by G over 6 pi eta r. Excellent. Did you make more progress or was it just
Yeah. So then I wrote down. So I wrote down the equation for V. So 4/3 pi r cubed.
Excellent.
And
So
then,
he noticed, let's explain to everyone. So what you were saying, he noticed that in the final equation, there's radius, but there's no radius here. So where can I get the radius from? Oh, I could get the radius from the volume because volume is related to radius. So he said, okay, it's a sphere. So volume is 4/3 pi r cubed. Excellent. Carry on.
yeah, so to get r squared, you can cancel the r at the bottom and then the r cubed to get r squared. So
Okay,
I did
so
that.
let's first of all, let me factorize out v and g. Why am I
Yeah.
doing that? Because they both share the same factor. So this becomes v g pb minus pf. All of a sudden, I'm really happy because there's pb minus pf on the original equation. So I know I'm onto something. So vg pb minus pf over 6 pi beta r. I need to start making some space. I'm going to rub out whatever I have on the right. We'll take this to the right. Good. Now let's substitute the volume in. Let's substitute volume is 4/3 pi r cubed. So that becomes velocity is 4/3 pi r cubed multiplied by g multiplied by pb minus pf over 6 pi viscosity radius. Okay, now there's a lot of simplifications to be done. The first is, as you told me, the radius cancels out because there's r cubed over r, so that just becomes r squared. And I know there's an r squared here, so I'm happy. What else can we do?
Cancel out the pi's.
Cancel out the pi's. So let's write that down. So v is equal to 4/3 r squared g pb minus pf over 6 eta. Now, Joanne's going to tell me, what can I do now? What's the difference between these two?
Well, oh yeah, we gotta divide, sir. Like because like everything else is fine.
Mhm.
But we need the 2r squared and the 9 with the so we're not sure. Oh no, wait, we gotta multiply by 3. No.
No, you were onto something. So this is 2/9, but this is 4/3/6.
We divide both sides by 4/3.
Or you just literally write down what is 4/3/6. Mathematically,
Yeah.
that's the same as 4/3/6/1. So you multiply the stuff farther apart and you multiply the stuff closer apart. So that becomes 4/6/12/18, which is the same as 2/9. Or if you didn't want to do that, you could just do 4/3/6. If you ever see a fraction like that, you multiply these two. So that's the same as 4/24, which again gives me 2/9. So actually 4/3/6 is 2/9. So now I just replace that with velocity is equal to 2 r squared g pb minus pf over 9 eta. Raise your hands if you were able to follow. Good. Excellent. And don't worry, I have literally derived it all for you on some nice little notes I've made. So let's do one last little look. So a ball falls through a liquid with viscosity eta until it reaches terminal velocity v. At terminal velocity, the forces are balanced. So upthrust plus viscous drag is equal to weight. So mf, the mass of the fluid, times g equals 6 pi blah, blah, blah. I know that the mass of the fluid is the density of the fluid times the volume, and I know that the mass of the ball is the density of the ball times the volume, and the volume is the same. So that the equation becomes 6 pi eta VR equals this. I rearranged to make V the subject. I did it over here in a slightly different order, but you end up with this. So this I'm going to upload in the classroom as well. And I want you guys to all memorize how to derive this, because there's so much different possible questions they could test you on that involves you understanding how to derive it. Okay, so it's very important you learn how to derive it. You don't need to memorize this equation for terminal velocity, although you probably will memorize it if you keep practicing how to derive this. But what you do need to memorize is, how do you go from this balanced equation? How do you go from this to this? This is something you do need to know, and it has come up in the past, a long time ago, as a 5-mark question. And if 5 marks is the difference between an A and a B, yes, your grade boundaries are literally like that. In fact, sometimes 4 marks is the difference between an A and a B, or a B and a C, or a C and a D. So yeah, you can't skip this. Anyway, let's carry on. Let's carry on, and so you want a spherical object to travel as fast as possible through a liquid, meaning you want it to have the fastest terminal velocity. Okay. First of all, sorry, where is it? First of all, what variables can you change to make sure the terminal velocity is as fast as possible? What variables can I change? I want a ball falling through a liquid to travel as fast as possible. What variables can I change or manipulate? Okay, I'll start you off. I could increase the radius of the ball, because looking at this equation, the velocity is proportional to the radius squared. So the larger the radius, the faster the ball is going to fall. What else can I do?
So you can use a ball that has a greater density.
Good. You could
then
use, yeah, beautiful. So you could use a ball that has greater density, because velocity is proportional to the density of the ball. What else can we do?
Make it travel in a liquid with a low viscosity.
Good. So because the volume is inversely proportional, the velocity, sorry, is inversely proportional to the viscosity. What I can do, if I want to increase this, I need as small viscosity as possible, because I want to divide by a small number. I don't want to divide by a larger number. So I could reduce the viscosity of the fluid, and that kind of makes sense, because if there's less viscosity, there's less frictional forces opposing the motion. So you have a higher acceleration. Beautiful. What else can we do? One last thing. So increase the radius, increase the density of the ball, decrease the viscosity. What else can we do? What variables have we missed from the equation?
So could you say density, decrease it?
Decrease the density of what?
The object, the spherical object.
No, you want to increase the density of the object, but you want to decrease the density of the ball. Let's explain this. Sorry. You want to increase the density of the ball, which is the object, but you want to decrease the density of the fluid, because PB minus PF. Okay, if the density of the fluid is less, you're subtracting a smaller number, so your overall value is going to be higher. Does that make sense? So you want to decrease the density of the fluid or increase the density of the ball. And the last one is perform the experiment in a planet with a larger gravitational field strength, I guess. Because yes, G is 9.81, but that's only in Earth. So if we perform the experiment in Jupiter, then we'll have a higher maximum velocity. Obviously, that's not very realistic, and obviously never talk about that in your exam, because you have to be somewhat realistic, but it is still a variable. Okay, now, what is the equation for viscosity? I know what the equation for the terminal velocity is, but how can I work out what the equation for viscosity is? Well, you could just swap the viscosity and the velocity around. So how did I do that? I just swapped these two. And how does that work? Well, that's the same. When you take the viscosity to that side, you're going to be left with velocity times by viscosity is equal to 2r squared g pb minus pf over 9. You want the viscosity to be the subject, so just divide this by velocity. So 9 times velocity. So that is the equation for viscosity, because you might get thrown off in the exam. You might be so used to deriving the velocity, and the exam might randomly ask, derive the equation for the viscosity. So you do the same thing, but you make the viscosity subject at the end. Okay. So let's move on. Let's say we want to perform an experiment to work out the viscosity of a fluid, maybe honey, maybe oil, maybe water. We want to work out the viscosity of the fluid. And we know the equation for viscosity is 2r squared g pb minus pf over 9v. So we know the equation. So what variables do we require? Well, we require the radius r. We require the density of the ball, pb. We require the density of the fluid, pf. And we also require the terminal velocity of the ball, v. We know what g is, it's just 9.81, and 2 is just a constant, 2 is 2. So those are the variables you need to measure or work out or deduce in order for us to work out the viscosity of a fluid. And once we know these variables, we could plug it into the equation and we could work out the viscosity. Now the question is, can you think of a method to determine each of the following above? So let's start with the radius of the ball. How can we work out the radius of the ball? Any ideas?
So do you use the formula 4 over 3 pi r cubed, and then you like
This
make
experiment.
I don't know, so I don't know. Never mind.
No, excellent. I really like what you're doing, but to use that equation, you need to know what the volume is. How are you going to work out the volume? Right, so you can use 4 over 3 pi r cubed, but that requires you to know the volume. I'm talking about like you're in a lab and you're doing this experiment and you have a ball. How are you going to tell what the radius is? What are you going to do?
The radius, so you can't just measure the circumference and just divide it by 2.
Good. Measure the circumference, divide by 2. How do I measure the circumference? Or don't say circumference, say
A
diameter.
vernier caliper.
Good. A vernier caliper or a micrometer. Excellent. So you want to measure the radius using a micrometer or vernier caliper and then divide by 2. So you can measure diameter using a micrometer or vernier caliper and then divide by 2. Why shouldn't you use a meter ruler?
Because
So
like it's a
in
sphere, it's
case.
like
Yeah. Well done, both of you. Because it's too small. And remember, you need to use a small ball. What happens if you use a big ball? Then you're going to have turbulent flow. And one of the assumptions for Hooke's law to work and for us to use F equals 6 pi eta VR is that it has to be a small spherical ball traveling at a laminar flow, smooth flow. If you have a large ball, it's not going to be laminar, it's going to be turbulent. So,
Sir?
yes.
So I'm confused. How does dividing the circumference by 2 give you the radius?
Not the circumference, the diameter.
Okay. Because
Has the ball, has your vernier caliper, okay? As well with the ruler and the vernier caliper. You measure the diameter using the vernier caliper. and then you divide by 2 to get the radius. Okay, good. So that's how we do the radius of the ball, and that's why we shouldn't use a meter ruler. By the way, take notes as I go along, because I don't include the answers on purpose on the PowerPoints, because I discourage laziness. Laziness is the best way to fail physics. You always have to be using active recall and remembering stuff yourself and forcing yourself to not look at the mask scheme and figure it out on your own. But anyway, why is it important to correctly calibrate the micrometer or vernier caliper before using it?
So if it has like the 0 error thing, you're gonna get an inaccurate answer.
Good. So to avoid systematic error or 0 error. What does it mean, systematic error? This is the new word you're going to have to use for your spec. So systematic, meaning you're going to get the same error for every measurement. So let's say I get on a scale, and the scale, before I even jump on it, it reads 650 grams. I didn't even get on it. Then I get on it and I get a mass of 50 kilograms. What's my actual mass? Well, it's going to be 49.35, right? Because it added 650 grams before I even got on. Now, if someone else goes on it and he weighs 100 kilograms, what's his mass going to be? It's also going to be 100 minus 0.65. So it's a systematic error because this error is going to exist for any measurement. It's the same sort of error. So this, you're right. So there'll be a 0 error on your micrometer or your vernier caliper. So you have to calibrate it. You have to calibrate it such that when it's closed, so here's your micrometer, is closed, such that when it's closed, it reads 0. Sometimes it's closed and it reads 0.2 for some reason. So you have to calibrate it. So when it's closed, it reads 0. So and that avoids systematic or 0 error. Very, very well done. Next question is, what is the resolution of the instrument used? Do you guys know what resolution means? No? Resolution is the smallest possible measurement an instrument is able to measure. So for a meter ruler, what would the resolution be?
Sure, does it go down to millimeters, I think?
Yeah, the precision, sorry, the resolution of a ruler is 1 millimeter or 0.1 centimeters, because that is the smallest possible marking. That's the smallest possible measurement. Look, 1 millimeter, 2 millimeters, 3 millimeters, or 0.1 centimeters, 0.2 centimeters, 0.3 centimeters. So that's what the resolution is. It's the smallest possible measurement. For your micrometer, it's around 0.01 millimeters. Depending on the micrometer and vernier caliper. Obviously, different micrometers and different vernier calipers have different resolutions. So it says on your actual micrometer, so here's how a micrometer looks like. It has that little thing here. So it says on your micrometer what the resolution is somewhere like on the side. So that would be the resolution. In your labs, I think it's 0.01 millimeters. So yeah, that is the resolution of my micrometer. Let's carry on. How would I work out the density of the ball?
Sir, density is mass over volume. Use that.
Excellent. And how would you work out the mass of the ball?
Sure, like you would put it on a scale. Would
Don't
you?
say scale, because the ball is very light. So say electronic balance. Right?
Okay.
Because they are a lot more sensitive. So yeah, use electronic balance to work out the mass. How about the volume of the ball?
Displacement method, I think that's what it's called.
The ball is very small, so not very accurate method. I mean, what did we do in the first step? What did we work out? The radius.
What? Yeah.
Right? So can we use the
yeah,
radius?
yeah.
Yeah, so just do 4/3 pi r cubed. That's a lot more accurate than doing the displacement method because remember the ball is really, really small. And if you use the displacement method, you're going to use a measuring cylinder, and a measuring cylinder has a precision of 1 milliliter. Okay, 0.01 millimeters, which is the precision of your micrometer, is a lot smaller and a lot more higher resolution than that of a measuring cylinder. So your measuring cylinder, if you were to place this very small ball, it's only going to increase by a small amount, and there's parallax error involved. There's also bottom of the meniscus error involved. This is not a very, very practical method to do. So you're going to do 4/3 pi r cubed. Nevertheless, fantastic suggestion. But in this context, no. In another context, maybe when we had a larger object and it's not as fair, it's an irregular object, then yes, 100% please do use the displacement method. Okay, let's continue. So mass over volume, the mass can be measured using a balance, and the volume is 4/3 pi r cubed. What must we ensure before measuring the mass of the ball? Do we just slap it on the balance straight away?
Sir, do you have to make sure that there's no syntax error or systematic error, not syntax, sorry.
Yes. Systematic error, very well done. We're not doing coding, so good. Adjust or calibrate the balance so there is no zero error, there is no systematic error. So it reads 0. Very well done. Because I'm not sure if you've seen an electronic balance, you always have to press reset at the start, don't you? So it reads 0. So there's always like that extra reading. So you always press reset and then it reads 0 and then you place your object. Good. The balance must read 0 to avoid systematic error, which increases accuracy. The density of the fluid, that's your third variable. How do you work out the density of the fluid? Don't say 4/3 pi r cubed for the volume. Who wants to suggest something else? So obviously density is mass over volume. How do we work out the mass of the fluid? Anyone?
So you take like the mass of the container it's in first, and then with the liquid and subtract the two.
Good. So first you measure the mass of just the measuring cylinder using your electronic balance. Make sure there's no zero error reading. And then you add the fluid and you measure the mass of this plus this, and then you subtract the two. Fantastic. How do you work out the volume of the fluid?
Just use like a measuring cylinder or something like that.
Yeah, it's in a measuring cylinder. So just take a reading at eye level in the bottom of the meniscus. Excellent. Now we know what the density of the fluid is. Your exam could test you in any of these little details. Any of these little details. And there's 3 required practicals where you need to know all the little details and intricacies. There's Young's modulus, there's viscosity, and there's the acceleration one using the light gates or a camera or whatever method you use. Okay. And the mass using an electronic balance. The volume using a measuring cylinder. Okay. What should you consider when measuring the volume of the fluid? You measure at eye level and bottom of the meniscus, but the main one's eye level. That is the main error. Make sure you measure at eye level. How can I make sure I measure at eye level? I could use a set square. Always, when you want to measure something at eye level or parallel, then you have to use a set square. The final one and the hardest one, and the one that takes the most effort in the actual practical, is the velocity of the ball. How do I measure the velocity or the terminal velocity of the ball?
So what's it called? You could use an automatic timer and drop it from one point, and then so you use 2 automatic timers. You drop it from one point. You have like a specific distance, for example, like 10 meters. So when it starts, the automatic timer starts itself, and then when it reaches 10 meters, it will stop, and then just do speed because distance over time.
By automatic timer, are you referring to a light gate?
Oh yeah, light gate.
You can't use a light gate for this experiment. Why? Because your light gate looks like this. There's one light gate here connected to a stand, and there's another light gate here. The light gate involves there being nothing in it, and as soon as something crosses, it triggers it. But the problem is everything's happening inside the measuring cylinder, so that will constantly trigger the light gate. Plus, you can't really fit the measuring cylinder between your two light gates, can you? So fantastic suggestion. And if we can use a light gate, that will make our answer so much more accurate. But unless we somehow put the light gate inside the water, which is a bit dangerous because there's electricity involved, we can't use a light gate. So what else can we do?
Sir,
Yes, John.
could we just do it like as it says in the picture, like legit just mark where it starts, mark where it's finished, like for example saying, let's say 10 meters, we take various timings, like let's say to remove human error, or what was the other name?
Yeah, it will be human error and parallax error when measuring the distance.
Yeah, and we could just take various timings and just work out the average from that to get a much
Good.
accurate solution.
Average repeat is a very wise option. So yeah, use a stopwatch to work out the time. You use a ruler to work out the distance. You do distance over time and you get the velocity. But there's some intricacies involved. And that is, shall you place, where is it? Which 2 points should be used to measure the distance? V and W, X and Y, W and X. What 2 points shall we use?
X and Y, I think.
Why not Y and X? Why not W and Y?
So it's too close to the surface. Like once you drop it, it's gonna be hard to like when you because you're doing it, we're using a stopwatch, right? So it's gonna be hard to start it.
These
like,
sort of
measure
vague questions that are not really true are never worth a mark. And hopefully in like a month or two time, you understand what I'm talking about. These sort of like wishy-washy answers. The answer is always clear and not vague at all. It's not to do with that. It's to do with something else, and it's to do with something physics. What is the velocity? Is it any velocity? This equation, what does the V stand for?
terminal velocity.
Terminal velocity. Do you reckon it reached terminal velocity at W? No, right? It's too slow. The friction is too little. The friction is not equal to the weight. So it hasn't reached. So you need to give it a little bit of time for it to reach terminal velocity, and then you want to start the stopwatch. Otherwise, you're not working out the terminal velocity. You're just working out the average velocity, and it's going to make your answer inaccurate. So good. And we'll end the session here. I'm going to upload questions on Stokes's law density up first for you guys to do for homework. And then I'll see you all on Thursday at 4 p.m. Any questions? No? Everyone's happy? Okay, I'll see you all on Thursday.